Okay. I write down proposition 7.4.1 in textbook, but the statement is more general or more complete than that provided in the textbook. Okay. So xy be two independent random variables, and g and h are two piecewise continuous real valued functions on R. So that's g of x and h of y are random variables. And so if either gx and hy are non-negative, or if any of them is not non-negative, then we would require that the expectation of g of x and expectation of h of y exist. Okay, sorry. Exist and are finite. Okay, so we have two conditions. Then for two, the expectation of the product of these two random variables exist and is finite. Okay, this is for two, because for one, the product is non-negative, so expectation always exists. Okay, and for both 1 and 2, that the expectation of their product is equal to the product of their expectations. Okay. Yes. Any question? No. Okay. Sorry. So the proof. This follows from propositions. I think it's 6.3.D. E. And 7.2.A. Okay. The proposition at 6.3.E indicates that because x and y are independent, so gx and hy are independent. Okay, they are independent. And the proposition 7.2.A we proved last week just give us this statement. Okay. Okay, and now I would like to state a proposition 7.4.D. Yep. X a random variable. Okay. Now, if we have two positive numbers, so x and r are positive, and both of them are bigger than or equal to 1, and r is greater than or equal to x. And if we know that the S power of the S value of x is finite, then the expectation of the S power of the F value of x also finite. Okay. All right, so let's prove that. Okay. Observe that if if we have two real numbers, okay, okay, for all x greater than or equal to 1, all right, x to the s power will be less than or equal to x to the s power. Okay. Right? That is a simple property of real numbers. Right? Any questions? Okay. So if no, all right. So let's see. Expectation of s power. Okay, can be expressed in two ways. The s power times the indicator of x is greater than or equal to 1. Okay, times it plus maybe for indicator of x less than 1. Okay. The sum of this indicator is equal to 1, right? Is 1. And so linearity of the expectation for non-negative random variables, because for non-negative random variable we don't care about whether the expectation is finite or not, right? Just we can have any linearity. So this is plus expectation okay, maybe I for my purpose I just change the order. Okay, that. Now, the indicator is 1 when what? When the absolute value of x is less than 1. But if the value of x, the function value of x is less than 1, then when you raise the s power, because x is greater than 1, so that this power is less than 1. Okay? Less than 1. So that this is expectation of okay, and plus expectation of x sinks for all x as far as less than 1, 2. Okay. Maybe you don't like x, you may you do. Okay. Because x is greater than or equal to 1. If x is less than, but well, I think that's true. Okay, for any s. Okay, and okay, now but the indicator so that this is it is 1. Okay, and here when x the absolute value of the function x random value is greater than or equal to 1. Now, so that in that case, then the s power of the s value of x will be less than the R power of the absolute value of capital X. So this is equal to all right. Okay, and so this is equal to 1 plus expectation of XR. Okay, because the indicator is either 1 or 0, so that so this random value is greater than or equal to this random variable, and this is finite, and we have that. Okay. Any questions? Hmm? Which one? That's fine. We always use for here we use proposition 7.2.8. The comparison. Huh? Proposition 7.4.8. Okay. Because in this proposition, when a random variable is bigger than the other random variable, then they have the same, they preserve the order for their expectations. And we have two versions, one for non-negative random variable, the others for random variables with finite expectations. And in here, we just apply, I think, the part 1, right? Okay. Because this random variable is greater than or equal to this random variable for every omega. You can test for every outcome the value, because this one is either 0 and 1, right? But this is always, when this is 1, okay, when this is 0, of course this is 0, of course. When this is 1, then the value would be maybe less than 1. Okay, so we have that. And again, both of them, we apply proposition, the same proposition, 7.4.8. Okay? So we apply the same position because the 1 is bigger than the indicator. Okay? And finally, this one is bigger than this one. Okay? And the last one is this one is bigger than this one, greater than or equal to this one, right? So we apply proposition 7.4.8 several times. Okay? So proposition 7.4.8, even though very simple, but very useful. Okay? Very useful. And depends on how do you use it. Okay? How do you use it? Okay. So my device is that I decompose the 1 into 2 parts, right? And to do my derivation. Okay? When we have a good choice, you have to make a design to use the tools, right? Otherwise, a good tool, if not used, is nothing. That means no tool at all, right? Okay, any question? Okay, so So what is the significance of this proposition? All right. So proposition 7.4.d implies that if a random variable has if a random variable x has nth moment, has finite nth moment, i.e. expectation of okay. So if a random a random variable has finite nth moment, then x has finite mth moment for all for all low order. So if a random variable has second moment, then it will have first moment, means that it will have finite expectation. And if a random variable has fourth moment, has finite fourth moment, then it will have finite third moment, and finite second moment, and finite first moment. Okay. Okay, so now we are able to define covariance. The covariance between two random variables x and y, okay, having finite second moment. Okay, so x and y are two random variables having finite second moment. Okay, and then the covariance, all right, denoted as, so the notation is COV of x, y is defined as here defined to be the expectation of the x minus ex, y minus ey. Right? Now, this definition has no ambiguity. Why? Because x and y have a finite second moment, so they have a finite first moment. Okay, so expectation of x is a finite number. Expectation of y is also a finite number. Okay. Okay, and this one, their product also has expectation. Right. This is because from so if we expand it has finite expectation, y has finite expectation, x has finite expectation. So their linear combination also has finite expectation by linearity of expectation we proved before. Okay. All right. So it is well defined, and furthermore, you can see this is equal to okay. where finite by Schwartz inequality and both EX and EY exist and are finite. By proposition 7.4.d. Okay? All right? So that means we are well prepared for this definition. Without the previous preparation, we have a lot of questions about this definition. Okay. Any questions? So this definition, not only a definition, but also give us a way to compute it. Okay. And we can see that if x and y are independent, then by proposition 74.1, we know the expectation of xy equal to expectation of x and y. So I have to say, furthermore, okay. This means that we carry over the sentence here that x and y have finite cycle moments. Okay, but furthermore, we know if x and y are independent, then by this proposition, we know that the expectation of the product of x and y is equal to the product of their expectations. So when we plug it into here, and the covariance of x, y is 0. Okay. You cannot just say that any two independent random variable has 0 covariance, right? Because x and y may not have finite expectation, right? So you have to say, for two independent random variables with finite cycle moment, okay, then that's good, right? Or at least x and y have finite expectation. Okay, at least. Why? Because by proposition 74.1, if x and y have finite expectation, then this expectation exists. Why? Because it's equal to the product. Okay, and by this definition, because you can compute them. So the difference is 0. Okay, so at least you have to know that two independent random variable with finite expectation have 0 covariance. Then that is correct. Okay, but covariance of x, y equal to 0 does not imply that x and y are independent. Okay. So this is just a necessary condition, not a sufficient condition for independence. We may take an example. So we consider consider a random variable x with the distribution. Okay, so we make it as simple as possible. Right, so x is a simple random variable. The possible values are -1, 0, and 1, and equally probable. Okay, and a random variable y defined by. So y is defined in the following way. It's 0 or 1. So if the x random value has value 0, then the y random variable has value 1, and otherwise. Okay, so i.e. y actually is indicator that x is equal to 0. You may think about that. Okay. Anyway, so I have two random variable x and y, right? Now we compute. So we compute them. When we compute it, you see that because y is the indicator of the event here. So what can you see? When the indicator is 1, then x has value 0. So 0 times 1 is 0. When the indicator has value 0, okay, of course the product is 0. So that this is the expectation of 0, and it is 0. Okay. Very simple, right? So the expectation of x times y is 0. Okay. And also we can compute x. You see from here, you see that this is 1/3 minus 1 plus 1/3, 0 plus 1/3, 1. So it's 0. So this implies that the expectation of x times y is 0, and is equal to ex and ey. You don't need to compute y, right? Okay, so this implies that covariance of x and y is 0, because 0 minus 0 is 0. And so now we inspect, are x and y independent? Well, so you can check. For example, x equal to 0, and y is equal to to 0, okay? The joint probability. These two events cannot occur simultaneously. Yep. Because when x equal to 0, y should be equal to 1. Right? So that this is 0. But this is not equal to 1/3 times 2/3. Why? Because probability of x equal to 0 is 1/3. And the probability of y equal to 0 is when x equal to 1 over minus 1, so it's 2/3. Okay, and so there you can see not equal. So this implies that x and y are not independent. Okay. All right, so that is a simple example to see the situation. All right, another proposition, a simple proposition, but I have to raise it up. X, y, two random variables with finite second moment. Okay. So each of them has finite second moment. Okay, and the AB, two real numbers. Then AX plus BY is a random variable with finite second moment. Okay? So proof as an exercise. Hint, use Schwarz inequality. Okay. All right, so it is an exercise. So what you can do linear combination of random variables having finite second moment, and the result, all right, the new random variables should have finite second moment too. Okay. All right. So now we will list some basic properties of covariance. The first one is covariance of xy is equal to the covariance of yx. Second, the covariance of x with itself is just the variance of x. Third, covariance of ax and by is A times B covariance of xy. Fourth, covariance of sum of n random variables of xi's and another sum of m y j random variables. So the sum may not have equal number, right? Here we have n x sub i's, but there we have m x sub j's, y sub j's there. Okay. And it's very interesting that it comes to the double sum of the covariance of x sub I and the y sub j. So they are n times m summand. Okay. So the number of terms in this double sum would be n times m. Okay. The first property is obvious from the definition. Okay, you can exchange the order of the product, right? Because they are real numbers. And if y equal to x, if y equal to x, this is the second moment of x, and you have the square of the first moment. So that is the definition of variance. So 1 and 2 are obvious. And the third one, you just plug in to here, ax and the by, ax, by. And because of linearity of expectation, so ab can move out, a move out, b move out, right? So you have ab. Okay, so no problem. So 1 to 3 are quite easy. Okay, and the first one, well, needs some calculation. Okay. But again, it's from the from linearity of expectation. Okay. So so maybe we can prove. So 1, 2, 3 are 4. Okay. We just compute. So by definition, this is the summation okay, so we just plug into this formula here. Okay. Now the product of two sums become two double sums of product. Okay, it's here. And by linearity of the expectation, so this is here, so from 1 to m, expectation of yj, here. And so now we move Of course, I have to say, okay. So of course I have to. Okay. So they all have finite second moment. Okay. So by proposition 74 E, we know that this sum has second moment, and this sum has second moment too. Okay, so that the covariance of these two sums must be finite. Okay. So there is no problem to do this computation. Okay, and here. Okay, and combine them. Okay, so covariance of xi, yj. Okay. Now, a direct application of the first item of the previous proposition. So from proposition 7.4.2.4. Okay, dash, maybe I use dash 4. We have the variance of the summation x of I. Okay, so the variance actually is the covariance of the sum with itself. And so that we know this is becomes to j from 1 to n. Well, if you like, you can do it gradually. J from 1 to n and xj. Okay. So to represent another sum, you use the dummy index j. All right, other than the I. Otherwise, you will conflict to each other. So that you have xj. Okay, so you have that. And now you divide it into two cases. If I equal to j, then this is just the variance of x of I. All right, so that you can have this is when j equal to I, and the other is that if I and j are distinct. So they are possible that, that I I bigger than j or I less than j. Well, and by the symmetric property here, right? They are equal. So you may just determine, right, to write down only the covariance such that I is less than j. Okay, I is less than j. And the other one, because the other is covariance of xj, and or maybe you like here. Okay, maybe you like here that xi I is less than j, and so that the first place is xj and the second place is xi. So you and so that okay, so this is I from 1 to n, and this is the variance of x sub I. Okay, so you have that, and the other is 2 times I less than j, and in between 1 and n, and covariance of xi, xj. Okay. Okay. And furthermore, if x sub i's are independent, okay? So if x sub i's are independent, then covariance of xi, xj is 0 for all I not equal to j. And we have the variance of summation of I from 1 to n, x sub I is equal to the summation of the variance of x sub I. Okay. So we have this simple formula when the x sub i's are independent random variables. Of course, all this previous discussion assume that x sub I have a finite second moment. So let's take an example. Called a sample mean and the sample variance. x1, x2, to xn. Okay, so we have n id random variables with finite mean mu and finite variance sigma square. Okay, so suppose we have, so RID just means independent, identically disputed. Okay, random variables. So they have finite mean and the finite variance. And the x bar is defined to be the arithmetic mean of x of i's. Okay, so you sum over the x of i's and divide by n. And this is called the sample mean. Okay? Of x of i's. So the sample mean is a random variable. Okay, it's not a real number. Okay, so even though the name we use the mean, but because we have another word before it called the sample mean, so that this is a random variable. Okay. Okay, so what are and okay, first of all, the x bar, the sample mean has finite second moment. The reason is that it's a linear combination of xi's, and each x sub i's has finite second moment, right? Because the second moment of each sub I, okay. So from here, the second moment. So this implies that, which is the variance of xi plus the square of the mean. So this is, so we know that each x sub I has finite second moment. And so as a linear combination, a spatial linear combination of x sub i's, so x bar has finite second moment. And so it has finite mean and finite variance. So that's why we can compute. So these two numbers, they are real numbers, okay? So these two numbers, right, are finite. So, and the computation of the expectation is easy by linearity, okay? Right? So this is by linearity of expectation. And the mu, so this is mu, okay? So the sample mean, the expectation of the sample mean is the mean of each x sub I, okay? So in statistics, we usually call this as the ensemble. Okay. And how about the variance of x bar? Well, the variance of is the a scalar times the sum of x sub I. And the scalar here, we can apply the third property. We can apply the third property, right? So the variance is the covariance of itself. And we have the A and so X equal to Y, A equal to B, so A square. And so here is N square and the variance of okay, so you can say it's proposition 7.4.2-2 and 3. Okay, and because X sub I are independent to each other, and we just write down here, we have this one, right? So this is become 2. Okay, since xi's are independent. Okay, and so this I from 1 to n sigma square, and so this is n sigma square. So now the sample mean has some characteristic that no matter how many n you have, the expectation of the sample mean is always equal to the ensemble mean, the mu here. But the variance of the sample mean, well, inverse proportional to the size of the random number, the size of this is short sequence here. So as n goes to infinity, the variance goes to 0. Okay. So when the variance goes to 0, okay, the variance goes to 0, then the sample mean goes to the mu, okay, goes to mu with probability 1. Okay. But I will not go to this conclusion yet because we will discuss that concept in chapter 8. But you can observe that the sample mean has some statistical significance. Okay, if you want to know the true mu, the true expectation is an unknown parameter, okay, and you want to know it in hyper precision, then you can do random experiment with the same device, okay, to do the measurement. And you assume that each time, the measurement you do is statistically independent. There's no correlation at all. For example, you ask for people in different country or people in different group, or they are stranger to each other. Okay, they perform so that it would be an adequate evidence to say that these measurements are independent. And then you do the sample mean or sample average here. Okay, so if the number of people who perform the measurement is big, and we know the variance decline sharply, right? Become to a very small number. So the data should be very narrow, okay, because the variance is very small. All right, so the dispersion is quite small, and so that the sample mean will be very close to the true expectation. And you will get a very good estimate. Okay, of course, in statistics, So the statistician should be estimated the error. All right. So how big is the error? Okay. And I will make an example. Oh, okay. So, okay, right. So that has some statistical significance. Another quantity is to estimate the dispersion. The dispersion. So now the difference. Okay, the difference xi omega minus the sample mean. Okay, between the ice data and the sample mean is called the ice deviation. Okay, right? So we define the ice deviation is the difference between the ice data and the sample mean. So now the random variable. Okay, we call x square omega. So x square is not really the square of x, it's just a name. Okay, so you have to be careful. Okay, x square is together as a name. Okay, not the square of something, no. Is that okay? So defined to be summation of I from 1 to n. So is that you sum over all you sum the square of all deviation. Okay, so for each deviation you square it and you sum over all the n squared deviation and divided by n minus 1. So it's very strange. Why is n minus 1? You may wonder. Why not divided by n? Because in here it divided by n, but why is divided by n minus 1? Very interesting, right? And you will see why. Right. So the whole thing is defined to be a random variable. So x squared together, okay? Together. So x squared is something together, right? It's not the square of something. But of course, you can take the square root, then it becomes to s. But at the beginning, we just think about that. It's just a name, okay, of a random variable. Okay, so I purposely write down this random variable as a function of the sample space, right? So I express the value of this function at this outcome, right? So I deliberately do so, okay, to emphasize, okay, it's a function, okay. Now, so this random variable is called, right? It's called the sample variance. Okay, the sample variance, because it's just like a way to find the variance, but it's by using the data, right? To do. So sample variance, like a sample mean, is a random variable too. Okay, it's a random variable too. So now the Now we will explain why we use n minus 1 instead of n in the denominator. Okay? So what is S squared? What is the expectation of the sample variance? All right, the sample variance exists because that all involve second moment of xi and so you can see xi has a second moment, x bar has a second moment as we know. So the difference has a second moment. Okay, it's a second moment. So the expectation exists. Right? So now we compute. All right, and so note that we first note that if we multiply n minus 1 with s squared, we get from 1 to n x sub I minus x bar. Okay, we get this one. And it's a good practice to minus their mean. Okay? Because sample mean has the same expectation as the x sub I, as we proved before. Okay? So we can subtract mu, but they can cancel here, right? Okay, and the square, I'm sorry, I forgot to put it. And so we can expand it. We have two terms. So by binomial expansion, we have x sub I minus mu square. Okay? The other one is summation I from 1 to n x bar minus mu square minus 2 x minus 2 summation I from 1 to n xi minus mu and the x bar minus mu here. Okay? Okay, and we can simplify. You can see that the summand here are all the same. So you have n times x bar minus mu square. And x bar minus mu is a common factor, so you can factor out here. And summation I from 1 to n, and the xi minus mu here. Okay? Okay, and now you can multiply with n and divide it by n here. Right? And now so we take a look at this sum. So here you can do this 1 over n summation I from 1 to n x sub I is one term minus n summation I from 1 to n the mu here. And what is that? This is just the x bar, and this is minus mu here. Okay, so basically the sum here, when we extract n out from this sum is actually equal to this vector. Okay, so we have I from 1 to n x sub I minus mu square plus n x bar minus mu square, and here minus 2n x bar minus mu square. So you can cancel them, and so this is So now you have xi minus mu square minus n x bar minus u square. Okay? Okay, so after we do this calculation, now we take the expectation on both sides. So we have a minus 1 expectation of x squared equal to now by expectation minus n expectation of linearity of the expectation. And so, but this is just the variance of xi. And the xi has identical distribution. So this is n times sigma square. Okay? All right? And minus n. And what is the this is the variance of x bar. But the variance of x bar is sigma squared divided by n. We have already computed here. Okay? This is the variance of x bar. Okay. Okay, so you have a minus 1 sigma square. So finally, you have the expectation of the sample variance is equal to the variance of each x sub I. Okay, so this is because we expect the defined random variable whose expectation is equal to what we want to have. That means that the variance of each sub I, the parameters we want to estimate. Okay, so it's quite huge. It's quite common in statistics that we try to estimate the mean and the variance of such a sequence of IID random variables. And a good estimate for the mean is by using the sample mean, the x bar. And a good estimate for the variance sigma square is the sample variance here, defined in this way. Okay, and we can, as we have shown here, the expectation of x bar is equal to mu, and the expectation of the x square, the sample variance, is equal to sigma square. All right, so they fulfill our requirement, and the quality for the sample mean, we know that the quality is good because as n goes up, the variance of the sample mean decay, right? Inverse proportional to n, so they go to 0. Okay, and similar result you can compute the variance of s square, but it's more involved. Okay, more complicated. So I don't want to do it here. Okay, but if you refer to any statistics textbook, you will learn then the variance of s square to see the quality of that. Okay, so and I will take a break up to 2:45. Okay. Okay. I will check another interesting example. Sampling from a finite population. Right, so n, the size of a population of people. Okay, so suppose we have maybe in a city or maybe in our NTHU campus. Okay, so n is the size of a population. Now, and each of n people has an opinion about a certain subject. Okay? Right? So each of the n people has an opinion about a certain subject. And so VI is the VI is a real value. Okay, used to quantify the opinion of the ith person. Of course, I from 1 to capital N. So each person, right, in the population has an opinion, but we have to quantify its opinion. Okay, for example, recently, many parties they are doing the primary. Okay, so they want to find out suitable candidates for election in the coming December, and so they will make a phone call. Okay, now, so they will ask every person received for the phone call, say, do you like this candidate? And they want you quantify your likeness, like maybe 7 is the highest, 1 is the lowest, something like that. Right? So you have to quantify that. Okay, so VI is a real value used to quantify the opinion of the ith person. Okay, so every person in this population has an opinion and quantified as V sub I, a real value. Okay? And okay. Right, which is unknown. All right, which is unknown without questioning. Okay? So, and now it is often, okay, it's often interesting to know the population average called V bar of the population okay, maybe of the opinion, I'm sorry. Value V, but it's usually very expensive to ask every person in the population their opinion value. Okay, so basically, in principle, it's impossible, right? In principle, you could do, but the reality is that because the population is so huge that it's very expensive or difficult to ask every person in the population their opinion values. Because to find the population average, you have to know every V sub I and to compute this average. Okay, but each V sub I can be known only by questioning, right? So without questioning, you don't know what is Vi. So that is the okay. So people invent polling, right? So that's as an opinion poll, a group of n people, okay, will be randomly chosen from this n people, and will be questioned to determine their opinion value. Okay, opinion values. Okay, so now we have to establish a probabilistic model for this problem. All right, so X, the sample space, consists of all n select little n groups. Okay. Of n people. Okay, and the sigma algebra would be the policy of this is some space, but this some space is a finite set, so it's reasonable. And the P would be the equally probable measure. I.e., probability of an event is the size of x okay here. So the probabilistic model is very simple, just like here. Okay, it's reasonable because we assume the polling system is truly random. Okay. Of course, that every elections you will see party members criticize the polling system, say it's unfair to some candidate. Right. For example, the polling tend to poll more young people than the older ones, or vice versa, something like that. But that we don't count in that. We just assume that the polling system is really random. Okay. All right. So when this is really random, then this probability measure will be reasonable. Okay. So every group has the same probability to be selected. Okay, so that is the situation here. Pretty simple model here. Okay. I have to remind you, don't forget to establish a probabilistic model for your problem every time when you encounter a word problem. Okay, word problem. Now, we let x. So the sum of the unsampled opinion values. Okay. So that n x divided by n would be the estimate. So that an estimate of the population average VBA. Okay, so that is very reasonable, right? Because you select little n peoples from the population of n people, capital N peoples, and you question each of these little n peoples to get their opinion values, and the sum their values here. So for different group, you have a different sum, right? So that x is a random variable. Okay? So that x okay, so it's a random variable, right? And it's random because that the outcome of the sampling are random, right? They are different. So this average, this ratio, is an estimate. Okay. Okay. So now we want to now want to know that the quality of this estimate. Okay, the quality of this estimate. All right. So for now we will do the following analysis. Okay. So now with that, II. Okay, the indicator. Okay, so the indicator to indicate whether or not the ith person is included in the sample outcome omega, right? So this is a random variable, right? It's a random variable. So you can see II omega is equal to 1 or 0 if I is in omega, and otherwise if I not in omega. Omega is a group of n people, okay? Little n people. Always remember, right? So you have to know what is the probabilistic model. Okay. In here, every outcome is just a group of little m people. Okay? A group of little m people there. So you will not be a stranger than this notation, right? This is the ith person in this group of little m people. If here, then the indicator is 1. Otherwise, it's 0. So II, the indicator, is a random variable. Okay? It's a function from the sample space to the real numbers. Okay? If in your mind you don't have this probability space, then it's very hard to understand the notation here. Okay. So I have to pause a while to ask you any questions. Okay. We are go back to chapter 2 or chapter 3, right? At the beginning of the semester here. Any questions? Okay, so now if no problem with the indicator, then you will be successful at least 50%. Okay, up to now. Okay, so now x can be expressed for each group of little m people. All right. It's actually okay. So x is just the linear combination of the indicators, and the coefficient is just the opinion value. So you see that if the ith person is in this group of little m people, then its opinion value will contribute into the sum, right? if the ith person is not in omega, then it will not contribute to this sum. So this is exactly the meaning of the sum, right? So X is the sum of the unsampled opinion value. Okay, so this you can see here. All right. And now, once we have this, then things becomes to be easy. Okay. So now, expectation of X is bilinearity. It's VI and the expectation of EI. Okay? And the variance of X, right? Variance will be used to quantify the spread, right? The spread of the X. Okay. So that because this is a linear sum. Okay. So we will have variance of VI, II to summation covariance VI, II, Vj, Ij. Okay, so we have deduced this result, right? Previously, so we know that, and so we have summation. This is V sub I square, variance of II, plus 2 summation Ij, Vi, Vj, covariance II, Ij. Okay, so now we need to compute the covariance between II and Ij, and also we want to find the first moment, the expectation. Okay, so now we have to show the distribution. Because indicators either 0 or 1, so we just compute the probability that II equal to 1. The probability II equal to 1 is what is that? Is the probability of the omega in X. Okay, such that I is in omega. Okay, so this one. And this is the size of okay. Now this is capital N. Okay. Now you select a group of little n people, and this n little n people must include the ith person. Okay. So now, so the other n minus 1 people should be selected from n capital N minus 1, right? So that is the size of this one. Okay, and this is little n divided by capital N. Okay, and the joint distribution for all I not equal to j. So this is the probability that omega in S such that I and j in omega. Okay, and what is that? The size of all omega such as I, j is in omega. And what is that? That is n minus 2 minus 2. Right? Because in this little n, the group of little n people, 2, I and j must be in the little group. Okay, so the other n minus 2 person in this little group should be selected from the capital N minus 2 people. Okay. And why is that? This is the little n minus 1, capital N minus 1. Okay? So we know this because from this probabilistic model here. Okay, on this probabilistic model. Okay, and so now we are able to find the expectation of capital X. All right, so but first, expectation of EI is equal to the probability of, so that is little n divided by capital N. And the EI, EJ, the expectation of their product, because to compute the covariance, you know the covariance by definition, this one is expectation of II, IJ, minus expectation of II times expectation of IJ. Okay, so we have to compute this expectation. Okay, but this is probability IJ equal to 1. Okay, because this is also a 0, 1 random variables. Okay, and so this is the probability that II equal the indicator. Well, that's the same. II equal to 1, IJ equal to 1. So that is an okay. All right, and so the variance of II, okay, which is expectation of II square minus expectation II square. But expectation II square is equal to expectation of II minus expectation II square. So what is that? So that is n 1 minus. Okay, so that is the variance of II. And how about the covariance of II? Ij for I not equal to j. Okay, so this is expectation of Ij minus expect. Okay, so this is n. This is little n minus 1, capital N minus 1 minus little n square. Okay, and so that it becomes minus little n and capital N minus little n, and n square and n minus 1. Okay, so that is the covariance here. All right, so with all these data, so now we can write down okay, so that expectation of x is equal to summation I from 1 to capital N little I, and the expectation of EI is n divided by n. So what is that? It's n times 1 over okay. So this is n V bar. So this implies that expectation of x divided by n is equal to V bar. Okay, so an estimator, if we use x divided by little n as an estimator, okay, as an estimator of the population average, then we see that the expectation of this estimate is equal to the value we want. Wow, surprise, right? Very good. Very good. The expected value of this ratio, okay, is what you want. What you want. And the second thing is to know the quality. So to find the quality, we first know the variance of x. Now variance x from there, so this is equal to summation I from 1 to capital N, and the VI square, and here we have n capital N minus little n, and n square, okay, minus. So actually this is a constant, right? Because each II has the same distribution. So maybe I will write n capital N here, n square summation I from 1 to n VI square, okay? Minus, and this is will be the same. Covariance Ij, you can see it's independent of Ij. Okay, it's this number. So we have minus 2 little n capital N minus little n divided by n square n minus 1 summation 1 n and the VI Vj. Okay, it looks very complicated, but we can reorganize them, okay, by some patience. Okay, patience, so you can n divided by n minus 1, okay, and so that it's 1 over n summation I from 1 to capital N, and VI square minus V square. Okay. So that you can simplify into this one. And this is meaningful. Why is that? Well, you can see that this is a kind of sample second moment, right? Can you see that? The sample second moment, you can see. Because this is the square and take the average. And this is the square of the population mean. This is the population average, square population, and this is the population variance. So you can say, but population's second moment. Population second moment. Okay? All right, and this is the square of population first moment. So what is the difference? Becomes to the population variance, okay, right? You can define them as population variance. Okay, and this is not the end story, because we use the variance of x divided by n. This is what we use, right? And this is 1 over n square, variance of x. Okay, so the final thing is that that's capital N minus n divided by n minus 1. Okay, and okay. Okay, so you can see that the variance here is less than or equal to 1 over n times the population variance. Okay. The population variance is the fact, it's the truth, right? Because it depends only on the original data, right? So this population, right, has a population variance, so it's the ground truth there. But this polling effect, this polling estimate, from here we know that the variance is inversely proportional to the size of the sample. So that is very good, right? So if you invest more money to do the polling, means that if you increase the size of little n, okay, then you have a better quality, because the variance of this ratio is proportional, inverse proportional to the size of little n. The expectation always the same, the population mean here. Okay. All right. So this is the theoretical foundation of any polling system. Okay. And I hope you will believe that, because this is mathematics. And I believe that if the polling mechanism is truly random, if there is no cheating at all in the polling system, right, then this computation, this theoretical prediction, will be legitimate. And everybody should believe that, because that is mathematics. Okay? Otherwise, if you say that this is not true, then you have to say the polling system is unfair. Okay? Means that the chosen group has bias. Okay? And that is the other story. This is not mathematics. Okay? That is politics. Okay. All right, so I stop here. Okay.